Hi, I'm Renmil Patrick Villalomia.
Hi, I'm Kevin Chris A. Rosakdin.
Hi, I'm Amy Angela A. Moncada.
Hi, I'm Genesis Mar NPC.
And we're Group 2.
So our project here is about designing a digital calculator that will be implemented on a D1 FPGA board, which you can see here using Verilog HDL. What you will see in this video is the specifications of the said project. For the general overview, switch 9 here acts as the master reset of the digital calculator. If it is at high state, it will reset all values to 0 and returns the output ports to their default states and display like how the clear memory does in a real calculator. Switch 8 and switch 7 determines the mode the user wishes to use. When both switch 8 and switch 7 are at down state, the standard calculator mode is enabled. Switch 6 to switch 0 here is the binary input of the mode wherein the decimal equivalent is displayed at hex 2 to hex 0. Next, key 3 registers as an addition operation, key 2 registers as subtraction operation, key 1 acts as the equals operation which will be used to display arithmetic results, and key 0 is a clear button wherein it acts like an AC or all clear button. When I press this key 0, the display will reset back to 0 regardless of what input is registered. So for an example, I'll add 127 to 126. You can see here that 127 is displayed on hex 2 to hex 0. Key 3 will be pushed to register an addition and then 126 is registered at the switches. Pressing key 1 will yield an answer of 253 which you can see here. If I press the addition button again, I register a 127 and press key 1 again, the result will be displayed which is accumulatively stacking. Next, I reset the display and use subtraction instead. 123 is registered, then key 2 is pressed indicating a subtraction, and then 120 is registered and key 1 is pressed. This will yield an answer of 3. Subtracting 121 from 3 will yield an answer of negative 118 which you can see here. And from here, I'll continue adding and subtracting to verify the workability of the arithmetic operations. I'll continue adding until it reaches the 4-digit results, which is now the error indication of the mode itself. If the result of an arithmetic operation exceeds 3 digits, all red LEDs will light up, which you can see here, and the 7 segments display will display dashes. Notice here that to return to the normal display, key 0 must be pressed. I'll repeat the error indicator for a negative number, so I'll continuously subtract this until it reaches the error state again. For the next mode, when switch 8 is at low state and switch 7 is at high state, the base and converter mode will be enabled. Switch 6 and switch 5 determines what number system will be displayed at hex 3 to hex 0. If both are down, decimal is displayed. If switch 5 is up, octal is displayed. If switch 6 is up and switch 5 is down, base 13 is displayed. And when both are up, hexadecimal is displayed. The corresponding display can be incremented and decremented using key 3 to key 0 for hex 3 to hex 0 respectively. When switch 4 is down, the operation of the mechanical switches is to decrement. If it is moved up, the operation of the mechanical switches is to increment. So I'll just reset the display using switch 9 here. So for example, I want to convert, let's say, I'll just move this 1000 to octal. This is by moving switch 5 up. Display will then go to 1750 in octal, which is the octal equivalent of 1000 in decimal. If I move switch 6 up, then it will display the hexadecimal equivalent. When I move switch 6 down again, it shall return back to the octal display, which is again at 1750 and back again to the decimal equivalent. If I move switch 6 up from decimal, the base 13 equivalent will be displayed. So here I will decrement the hexadecimal equivalent of the previous example. Here, let's say to D0B7 in base 13. Okay, D0, B7 in hexadecimal. If I convert this to base 13, all red LEDs will light up and the hex 3 to hex 0 will display dashes. This means that the conversion to base 13 exceeds 4 digits, and thus increment and decrement is not possible. I'll again reset the display to convert a new number, which is FFFF in hexadecimal. So if I convert this to base 13, the error indicators must show, which you can see here, as well as when converting to decimal and octal. Also, during error indications, the display cannot be incremented or decremented like what I said. For the next mode, when switch 8 is up and switch 7 is down, logical operation is enabled. When switch 6 is up, 4-bit binary numbers can be stored in 4 variables depending on switch 5 and switch 4. Here, so I'll just move switch 9 to low. Here I press key 3 and key 0 to toggle hex 3 and hex 0 respectively. Also, LED red 7 to LED red 4 lit up, indicating the stored value at the first variable, which is when both switch 5 and switch 4 are down. If I move switch 4 up, LED red 3 to LED red 0 are lit, which is the storage for variable 2. I want to change its contents, thus I'll toggle the key switches to, let's say, 111, 11111. When switch 5 and switch 4 is up, LED green 3 to 0 lit up again, and I want to change its contents, thus I'll toggle the key switches to 0110. Finally, when switch 5 is up and switch 4 is down, LED green 7 to 4 will become the storage of the final variable. I'll set it to 1100. Since all variables already have contents, I'll move switch 6 to down and to enable the logic operations. Accumulator value starts at 0000, which you can see here at the display. The logical operations after key press will depend on switch 3 to switch 1 here. If switch 3 to switch 1 is down and I press any key switches, the accumulator value will be bitwise negated, which you can see here. It became a 11111. So for switch 3 to switch 1 at 001, the bitwise AND is activated. Switch 1 is at 100, the bitwise XOR is enabled. Here, if I press key 3, 0110 will be bitwise XORed with variable 1, which is 1001. This will result to 1001. Again, this is repeated for all variables as desired. When switch 3 to switch 1 is at 101, the circular shift left is enabled. Any key press will circularly shift the contents of the accumulator, like what you can see here. Pressing any of them will circularly shift left the accumulator. When switch 3 to switch 1 is 110 and any key press is pressed, the display will result to 1111. And finally, when switch 3 to switch 1 are all up and any key is pressed, accumulator value will set to 0000. Finally, the last mode is when switch 8 and switch 7 is both up, which is the BCD operations. Here, the variable storing function from the previous mode is still there when switch 6 is up, with the exception of displaying the contents at the LEDs. Again, switch 5 and switch 4 determines what variable will be updated. So for variable 1, which is when switch 5 and switch 4 are down, I'll store a value of 1001 here. Next, for variable 2, I'll store a 1000. And for variable 4, take note if the assigned BCD number is greater than 9, like what I did, hex 3 to hex 0 will display dashes and red LEDs will light up. So to revert back to the original display, I will again toggle the key 1 to go back to the normal display. So I'll assign 0101 for variable 4, and finally for variable 3, I'll store 0111. Now, when switch 6 is down, BCD operations are enabled depending on switch 3 to switch 2. Again, accumulator starts at 00. If switch 3 to switch 2 is down, the BCD addition is enabled. Like the previous mode, which is in the logic mode, accumulator value will update after key press. So here, BCD addition is executed for each key press and their assigned variables. So if I press key 3, which is 1001, or 9 in decimal, the value of 9 is shown. If I press again, it will go to 18, so it is just cumulatively stacking. Pressing key 2 will continuously stack until it reaches a number greater than 999. So in this case, which you can see here, hex 3 to hex 0 will display dashes and all red LEDs will light up. To revert back to the default display, switch 3 to switch 2 shall be up. And which is shown here. And next, if switch 3 to switch 2 is 01, BCD subtraction is enabled. So if I press key 3, it will display an error indication because 0 minus 9 is a negative number. In this case, again, switch 3 to switch 2 shall be up to go to the default display. Here, I'll just again add, and so here when switch 3 to switch 2 is 10, it will just retain the cumulative value. And finally, when switch 3 to switch 2 is both up, accumulator will reset to 00. Thanks for watching.